in Paris, Université Paris 6, mainly working on LHC data for the ATLAS experiment. Then she had postdoctoral position in Barcelona, working T2K collaboration, and a CERN fellowship and a project associate working with the neutrino platform, involved in ProtoDUNE-SP and the near detector upgrade for T2K and outreach activity for NP. Since 2020, August, so very recently, she joined the University of Geneva as a metro assistant working on the T2K experiment. Today, she will talk about ProtoDUNE-SP at CERN. So I'm turning my video off and I'll leave you discussing. Thank you, Stefania.
Thank you, Silvia. So it's, thanks also for inviting me for this seminar. It's my pleasure to present an overview of ProtoDUNE single phase experiment at CERN. This is actually, as I say in the title, a large-scale prototype for the first fire detector module of DUNE. So to start, a few words about DUNE. I'm sure that all of you already knows. So DUNE is a deep underground neutrino experiment, is one of the next generation long baseline experiment that are being prepared, and DUNE will be in the US, actually is under construction. So we will have a very intense beam from the LBNF facility. And so this beam will be shoot from Fermilab to South Dakota, so 1,300 kilometers away. So we will focus our attention for a moment on the fire detector. So this fire detector is so the schematic view is drawn here. So it's composed by 4 independent modules. One of these modules, for example, is this. And will be located 1.5 kilometers underground. So this module has very large size, as reported, for example, here, and will host of about 70,000 tons of liquid argon. So to go to this kind of large dimension, we had to do some prototyping, and that's one of the goals of the ProtoDUNE single phase. So ProtoDUNE, the single phase, is one of the 2 large-scale prototypes that are built and operated at CERN. It's one of 20 of DUNE module, and with this size dimension actually is the largest liquid argon single phase detector built and operated so far. So here is a technical drawing, how it looks like, and I will go through the details of the detector in the next slide. So here you have the outer dimension, so to be compared to the 1 dimension that I mentioned before. It hosts about 760 tons of liquid argon. And another point to keep in mind is that the ProtoDUNE single phase is taking data in zone surface. So there are several goals for this detector and this experiment actually. So the cryostat design validation, as well the validation of the cryogenic system. The detector is actually a prototype for the detector assembly, so it's really a detector engineer prototype. Also for the data acquisition and with the data taking, actually one of the goals is to fully characterize the detector response of this kind of technology with both particle species coming from a beam and also achieve possibly physics measurements. Here is a picture of the experimental area where the detector is at CERN. So this is the ProtoDUNE single phase with some cryogenic system here. And here far away, you can see the other prototype that is the double phase, but I will focus my talk on the single phase. So just a few words about the working principle. So we have an electric field that is applied on the inside volume. And when a particle passes through, so the argon is ionized and the electron, thanks to this field, are drifted toward the anode plane that is composed by three planes of wires. So in this way, we have a nice two-dimensional tracking, two-dimensional view of the event. But then we also have the information coming from the scintillation light. So actually the argon is also, the argon is, get excited. So they are excimer that are formed, and by the de-excitation of the excimer, we have the emission of scintillation light. And by the detection of this scintillation light by photosensor, actually we can determine the position of this event also in the drift direction. So in this way, we can have a three-dimensional reconstruction of the event. Coming to more details of the cryostat. So due to the very large dimension, we had to use a new concept for the cryostat, so not use anymore the vacuum, but the argon purge. And this actually came with a collaboration with the industry, so the GTT, that is a French firm, that actually developed a membrane cryostat technology something like 20 years ago. So it's well established, and this is used for liquid and natural gases transport ship and onshore storage. So this kind of technology, as I said, is well established and used since about 20 years, but has been re-engineered to answer the needs of liquid argon TPC detectors. Just to mention some of these needs, the fact that we need some opening in our cryostat to, for example, slide in the detector. So the picture that you have here is a view from the inside of the single phase the cryostat during the phase of the detector assembly. So this is a temporary opening that was allowing to slide in the part of the detector. We also have openings on the roof to allow the communication with the inside, the cryogenics also system, so cryogenics pipe, and also the support of the detector itself. So all this kind of opening actually were, let's say, modifying the initial design of the membrane technology, and has to be adjusted. So here in the figure, there is a sketch of actually this how this technology is done. So it's a series of layers that include, for example, 3 membranes and also 3 layers of insulation divided by plywood. And let's say the most important feature is this inner membrane that has this on the top of this peculiar shape that is actually a corrugation. So this is the part, this inner membrane is the one that you see here in the picture, and is the one that is in contact with the liquid. And this corrugation actually acts as a balloon to absorb the dilatation and the constriction during the change in temperature, when we move from room temperature during the construction to the cryogenic temperature. So to fully validate this new technology, there has been a very wide campaign to qualify each step of the construction and also of the operation of this new cryostat concept. And since this has been very successful, this campaign, since then there is a large employment of this new approach for several experiments. So this has been approved for the far detector module of DUNE, has been used also for the near detector of the short baseline program at Fermilab, and also for dark side. Going to the cryogenic infrastructure, so the system actually is composed by 3 main parts. So there is an external cryogenic part that is foreseen downwards to receive the liquid argon that is used for the filling, the liquid nitrogen for the cooling, and the hydrogen for the filter regeneration. Then there is the cryogenic proximity cryogenics. That was the one that was seen visible in the picture of the experimental area, so just aside of the cryostat. And this actually allows for the purification of the liquid argon and the rejection of the system, and as well also the purification of part of the boil off of the argon, its condensation and the reinjection. And then there is the internal cryogenics that is composed by pipes and manifolds that allow the distribution of gas and liquid argon. So here you can see some sprayers, for example, in the picture, and also the lines that allow for the injection of the liquid argon on the bottom of the cryostat. The cryogenic system in general has been designed considering the maximum flexibility for all operation to be adjusted and to allow for test during the operation. There are also, as shown in the picture here, some cryogenic instrumentation. So for example, purity monitor to monitor almost in real time the amount of impurity of the liquid argon, temperature sensors, two temperature sensors, and also, for example, camera that have been installed for visual inspection. For the cryogenic operation, we can divide, let's say, two periods. One for the preparation that consists of the purge, cool down, and filling, and then the normal or stable condition. So first, for the this preliminary part, we had the piston purge phase. So these actually allow, this consists on flushing gas argon from the bottom of the cryostat, creating a wave, a vertical wave that push air out. So the exhaust is vented out. And the velocity of the gas wave is actually a couple of times faster than the diffusion of air going down. And so in this way, we can reduce the air contamination to the order of a few ppm. Then this purged phase continues. There is just, let's say, the velocity of the gas injected inside that is diminished. And so this purge operation continues in open loop for about 44 hours that correspond to almost about 7 volume changes. And this allowed to reduce the contamination of oxygen and water to sub-ppm and ppm level respectively. After this purge operation conclude, there is the cool down. So gas and argon are injected via sprayers from the top that I showed before, and also from the line that are on the bottom of the cryostat for the filling simultaneously. And then this, especially the filling, so the injection of liquid argon from the bottom continue for about 6 weeks to reach the desired level. So here there are a series of plots that were done during the filling itself to monitor the rising of the liquid level, the gas, the good pressure, and also the temperature from outside of the bottom part of the cryostat, just to be sure that there were not a sign of any kind of leakage. There were also a couple of parameters to be monitored. So the maximal cool down rate that is set to 40 Kelvin per hour. And also, so the filling was done slowly to also satisfy this requirement to have a maximum temperature difference between 2 points inside the volume of about maximum 50 Kelvin. Now, once the cryostat was filled, we moved to a normal operation. And so we had a recirculation rate of the liquid argon via a lateral valve of for about that with a rate of about 7 tons per hour, and this actually allowed to have a recirculation of the full volume in slightly less than 5 days. So this liquid argon recirculation is done continuously, and the recirculation is done, so the liquid argon is also purified, passing through a series of filters. There is also a gas part. So actually there are two lines for the gas. One of these gas lines, so that correspond to about the 50%, is passing through another set of filters that are acting warm. Then the gas is condensed, injected in the liquid argon flow, purified again, and re-injected toward the bottom of the cryostat. And then there is a second line of gas that actually pass directly to the condenser and follow the line that I just mentioned. So these are the main purification system for the cryogenic. Now coming to the detector. So first, some introduction about the time projection chamber. So we have the time projection chamber is composed of two drift volumes that are separated by a central cathode. So we have an horizontal drift. We have an high voltage applied to the cathode of negative 180 kilovolt, and these actually provide an electric field of 500 volt per centimeter. The cathode, that is the one that you see here, is composed by 3 modules of this kind. And these are made of FR4 panels and laminated with Kapton. And then this instead is a picture of one module of the field cage that is actually made of aluminum profiles. In these figures, there is also, so this is one of the modules that are from the top or the bottom part of the field cage, and they also foreseen ground plane. For the readout, so we had wires, the readout made by 3-wire planes, and these are actually in 6 anode plane assembly. So this is the kind of structure that we have. So this APA, anode plane assembly. So this is how their wires look like. So there are warped wires and vertical wires. And this is a picture of one of the module of the one APA module before being installed in the cryostat. So we have to remind also that there is no signal amplification, and to minimize the noise, we used, so the electronic is installed in cold, so inside in the liquid arc. For detecting the light, we have the installation of a photon detection system. Actually, there have been 3 technologies that have been installed and operated in ProtoDUNE single phase. So all these 3 technology are based on light guide modules with a wavelength shifter and read by silicon PM. So these 3 technologies are actually installed in bar and installed in the EPA. So as shown here in the picture, and I will develop a little bit more the 3 technology in the next slide. So the aim has been really to understand the performances of these 3 different systems and define the better layout for DUNE. And each one of these APA has actually 10 of these parts. So coming to the details of these 3 technology. So we have a double shift light guide. So these actually have this shifting of the scintillation light a couple of times. And then by total internal reflection, the light is then read by a silicon PM array that is on one of the sides. The deep coded light guide is a really similar technology, but with just one shift. And again, a silicon PM array located on one side. And then there are the Arapuca technology. So these Arapuca technology are actually cells, as shown, for example, in the picture here. You see the small cells, and those cells actually act as light trap. So when we have the scintillation light that hit one of these cells, so this is first shifted. And if this shifted light doesn't hit the silicon PM directly, can hit actually the bottom of the cell where there is a TPB, so another shifter. So the light is shifted again. And here on the top, there is a decoy filter. So this shifted light actually cannot exit anymore this cell. So we'll go under reflection until he hit the silicon PM. This is a picture of the inside of the volume. So it's actually one of the 2 chambers. So here is the cathode that I described. These are the 3 planes that are sitting on one of the side of the cryostat. You can see the bars that are installed here that are the photon detection system, and here all around is the field cage. And so the drift length is about 3.6 meters. So the ProtoDUNE single phase has been following a very tight schedule. From the construction to the operation, everything was done in less than 2 years, and the goal actually was to have data with beam before the long shutdown 2 that happened on November 2018. So what then I have to mention is that together with the construction of the cryostat and the detector, we also had the construction of a dedicated beam line, or actually an extension of an existing beam line at CERN, as shown in the picture here. And so this allowed to collect data with beam, and also we achieve or we are actually preparing some physics measurement. And the first paper has been recently submitted in an archive and is being submitted to JINST. So in the figure here, you have a little bit some of the milestone during the construction up to when we were ready to operate ProtoDUNE with the beam line that you can see here. So this was September 2018. So we took a couple of months of data with the beam, and then after that we had about 2 years of data with cosmic ray runs, and we ended the operation at the end of July this year. The beam line, so this is in CERN jargon is called the H4 VLE beam line. So H4 is the name of the existing beam line, and VLE stands for very low energy. Very low energy is actually 1 to 7 GeV, but is very low with respect to the starting point. So the H4 beam line actually takes proton from the SPF. So we are of the order of 40 GeV. And so the H4 beam, so the beam line that goes to the single phase is actually a tertiary beam line. We collected about 40 million events with the hadron and the electron beam, as I mentioned on those momenta, but actually also low momentum for electron beam only on 0.3, 0.5 GeV/c. The beam line that is sketched here is also is instrumented, and so there is a time of flight and a Cherenkov counter to particle type that enters in the detector, and also wire chamber to measure the position of the beam and the momentum. And here is a plot that shows the time of flight versus the momentum of the particle. You can see how we can differentiate them with this information. The data acquisition. So this is also another important point for the TPC. We have two main systems. So the RCEs that was actually chosen as the baseline. So these come from a previous experiment at Fermilab, the 35 ton, and then Felix that actually came from development for the Atlas collaboration. So those have been taken data in parallel, but during the operation itself, Felix has been considered as valuable and reliable. And so the readout of all the APA actually have been switched to the Felix readout. Then the readout for the photon detection system is independent and done with another system. And the information coming from the photon detection system are actually one of the input for the trigger. So the trigger takes into account information coming or may take into account information coming from the photon detection system, but also from the beam instrumentation or the cosmic ray tagger that I did not mention, but actually we have upstream and downstream also panels that act as a cosmic ray tagger that we can use. So all those information goes to the central trigger board that aggregate the trigger inputs. And then there is a clock, the timing system that distributes the clock and align all the detector components. The data acquisition has also a farm that is composed with 20 high-performance servers that were monitoring the data flow and controlling the data taking on real time, and is also foreseen an on-site storage. And this is actually a temporary storage for the raw data before being sent to the long-term storage that is EOS at CERN or the storage at Fermilab. Coming to the performances, so for the time projection chamber, so this has been estimating using both beam data and cosmic ray data. There have been a pre-processing part of data to understand the noise and to prepare and to calibrate them, those data, and extract the ionizing signal. The performance of the TPC has been very stable. We had, and very successful, we have less than 1% of dead or noisy channel, and this number actually remained pretty constant during the 2 years of data taking. And also a very nice performance of the signal to noise ratio. Noise performance, so the very nice value for this signal to noise ratio, and actually very far away better from the with respect to the nominal design value. So this is a plot, for example, that shows this signal to noise ratio for the 3 planes of wires. So this black line, for example, is the collection plane, and the peak is slightly less than 50. And the nominal value or the goal that was for DUNE was of 9, so several times better than the design value. For the TPC, I mentioned that at the beginning, so that ProtoDUNE is sitting on surface. So actually is exposed to cosmic rays, and this large rate of cosmic ray entering the detector can creates what is called the space charge effect. So actually there is a large amount of argon that is ionized, and due to the fact that the ion moves slowly, those can accumulate and create distortion of the electric field, and also spatial distortion that act actually in stretching or squeezing the tracks. So the plot that you show here is like a top view of the detector. So X is the drift direction, 0 is the position of the cathode. The dotted line, the black dotted line is like the active volume, the position of the field cage. And you see these blue points are actually the points of entering and exiting of these cosmic muons. And so you see that close to the edges here, we have this bending of or lens effect. And this is actually due to the deformation of the electric field. Using data from cosmic ray, we have been able to build maps, 2-dimensional maps, and use those to generate 3-dimensional E-field maps, and to correct for those effects on data. And here on the right, you see the estimation of the distortion of the electric field with respect to the nominal value. Again, in a vision from the top. So you can see here around the cathode, and especially on this in this side, actually the beam enters on that side. We can have a distortion of on the maximum of about 25%. That's a large distortion. So there has been a really huge effort to understand and produce those maps to be actually used for as a pre-step for the data. Once this effect of the space charge are understood and taken into account, we also have to take into account other effects that may affect the calorimetric response of the detector, like, for example, the attenuation of the electron due to impurity or the electron recombination. And so take into account all of these, then we also have to then calibrate the detector. This is done using cosmic muon again. So we have to calibrate it first time. So we do the calibration in 2 steps. First, the response on the charge versus the X, and this is on the Y and Z coordinate as our first step. So we want to have this actually distribution well uniform. So once this is calibrated on these 2 directions, then there is a calibration of the DQEX on the X coordinate, that again is the drift direction. So you can see here, so this is before the calibration on the drift direction, and you can see that the charge is higher on the edges that correspond to the anode plane, and lower at 0 where is the cathode, that is what we expect. So because from the cathode we can have more acting of the impurities or electron recombination. So with the calibration of the QDX, we managed to have this distribution basically flat. And once this calibration of the QDX is done, then there is the conversion to an energy unit. And this is also the calibration in terms of energy. And this is done using the Landau and the Carvalho. So you can see the DX that we have for muon from the comparison data in Monte Carlo that are shown here. And as you see, the peak is well around 2 MeV per centimeter as expected. So when this calibration procedure is applied, we can then actually exploit the calorimetry detector response to different particle species. And as expected, we can have a high discriminating power of the DADX against the different particle type. So here you see the DADX versus the residual range. So the part of the track that remains, let's say, with respect to its end for proton and mu, and you can see that the distribution is very well separated. And the same information is plotted here as a chi-square. So you can see that the distribution of the muon is very well separated from the proton. And so the capability of to distinguish these two particle types is clear. Coming to the photon detection system, so we have calibration and characterization of the system as a main goal. Part of this, the studies of this step have been done using also an LED system that is applied on the cathode or installed on the cathode. This step, for example, concerned linearity in gain versus bias voltage, time resolution on the signal to noise ratio. And also we use beam data to exploit the calorimetric information of the photon detection system. The plot here below show the detection efficiency of the different technology. So you see the bottom, so in here, the points that correspond to the double shift and deep coated technology. And also here, the Arapuca that actually has a larger efficiency than two other systems. If we look, get a more close look to the Arapuca efficiency, this is what is shown on the plot here. We have actually a two distribution, and this is done by the geometry of the Arapuca modules, but it's especially of the Arapuca cells themselves. So there are in each Arapuca module, so in the bar, there are actually 8 cells with a window of a given dimension, and 4 cells with a window that is actually double. And this explains this difference in the efficiency by the geometry of the cells itself. Now we can also study the response, linearity of the response of the system with respect to the energy of the beam or the momentum of the beam particle, and this was done using electrons. Here, for example, is a plot that shows the number of photons detected with respect to the energy of the electron beam, and you see the very nice linearity. And from this plot, we can extract actually the light yield. So this plot is for the Arapuca, and we have a light yield of 0.1 photon per MeV. Then we can do the same study using the entire photon detection system of ProtoDUNE, and this is the curve here, and they correspond to 0.2 photon detector per MeV. And we can also do another exercise, so try to extrapolate what would be the light yield for ProtoDUNE if all the photon detection system was composed by Arapuca. And these are this is shown by the distribution of points here in blue. And this actually gave a light yield of 1.3 photon per MeV. That is, this value is actually, so this study shows the superiority of the Arapuca, together also with the plots of the efficiency shown in the slide before. And so you can compare this value with actually the DUNE requirement that was 0.5 photon per MeV. And so you see that the ProtoDUNE performance actually are satisfying the requirement of DUNE. Talking about the electron lifetime. So this is a very important information that we have to monitor. So to keep it this information under control almost on real time, there are purity monitors that are installed inside the ProtoDUNE, and these are installed on the volume, but outside the active volume themselves. We take run of the purity monitor several times per day, and these actually have very powerful information to detect or to know the impurity concentration, and also detect possible outage of the cryogenic system. The plot shows that is here show the electron lifetime coming from this purity monitor for the three of them that are installed at different height. And you see that are basically showing a flat distribution with a value of above 20 milliseconds, and this corresponds to impurities that are less than 3.5 ppt oxygen equivalent. You see there are some drops, so here there is a big one, but this is coming from missing data, and actually some other drops. One is coming from effectively a problem that we had on the cryogenic system. Other are coming from studies and tests done on the cryogenic system to effectively study the recirculation. The same kind of information of the electron lifetime can be extracted using tracks. And this is what is shown by on the plot on the right. This is the comparison between the measurement coming from the purity monitors and those extracted from the TPC measurements, and they are very well in agreement. So this plot covers only the period of the beam, so the months, the 2 months in 2018, while this plot actually covers a larger time window. But the message that I want to bring here is that with these two independent measurements, we can have a nice information about the real electron lifetime that we have, and the measurement are compatible. We study of the detector stability thanks to this large amount of data that we took, especially with COSMICS. And these allow to monitor the detector operational condition for the temperature and the lifetime that I just showed, but also the high voltage, for example, that is being in stable condition almost 99.5% of its uptime. And another nice information that we monitored doing all the data taking is the charge collected by the TPC, in the TPC. And this is being found very, very stable. So you see that there is mainly a flat distribution. There is a large deviation here. So this is actually this outage of the problem on the cryogenic system that I mentioned. And then there are other deviation, let's say, from this stable plateau that are corresponding either to decrease in purity that I mentioned from studies of the recirculation system. This was the first increasing of the purity. So we just switched on ProtoDUNE, and so we started to recirculate the liquid argon, so the purity improved little by little. And then there are some other effects that come from detector operation. So any deviation of this kind of plot are really well understood. And these show the understanding of and the performance of the detector. For the track reconstruction and moving to, let's say, high-level analysis, ProtoDUNE is taking data on surface, so there is a really busy environment that we have to deal with. So here is a event display showing the cosmic rays and one event coming from the beam. Actually, this was a pion. So we have an estimation of about 50 muons per event, and we use a very powerful algorithm that is Pandora to reconstruct the TPC information. This also allows to have a tag information to distinguish then cosmics and beam particle, and also define a possible hierarchy on the event. So it's really a powerful tool. So this, thanks to this powerful algorithm, we can address some high-level analysis. And for example, we are preparing several measurements. I would like to report about the preparation of pion and proton argon cross-section. So this is because there are almost no measurements that are existing in liquid argon. And the importance of this measurement is for the future DUNE neutrino analysis, because those measurements can actually help to constrain final state interaction systematics for DUNE. Here you have nice event display of some events for protons and pion. There are also other analyses that are being prepared. The Michel electron identification that are calibration standard candle for DUNE, pi-zero identification, and also thanks to the large amount of cosmics that we took, the seasonality of muons and a comparison with other existing measurements. So this is for the performance of ProtoDUNE and the analysis that are being prepared. But ProtoDUNE also serves as like a playground for R&D. There are several R&D that have been done. I will report just a few of them. So one is this, the xenon doping. So as we know, for detecting the scintillation light, we have to shift it. We're using usually we use wavelength shifter, and the xenon actually can act as a volume distributed wavelength shifter. So this can be very powerful and allow for uniform light distribution, and also help to increase the light yield and the detection efficiency. So the doping of with the xenon is not new. But was never done on a very large, on a large scale experiment like ProtoDUNE single phase. So this was actually the aim to understand the feasibility and the performance that we may have with liquid argon doped with xenon. To study the response to the xenon doping, then we had to insert new photon detection sensors in ProtoDUNE. So here is a series of sensors new sensors that have been inserted in ProtoDUNE. So you have to think about this like a vertical line. So we have two sensors that are called X-Arapuca. So this is like, this is a new version of the standard Arapuca that are installed in ProtoDUNE. That there is a silicon PM array, and then another technology with based on PEM fibers read by silicon PM. These two X-Arapuca sensors are not identical. There is one of these that actually is has a quartz window that allows to have sensitivity only to xenon light. So we can have the difference response with comparing these two photon detection systems. So the doping of the liquid argon has been done with 5 injection. And we reached a total of 13.5 kilograms of xenon that correspond about 20 ppm in mass. And the idea was to study then the light collected from the X-Arapuca and also from the other sensor that I mentioned, but also study the stability and uniformity of the response inside the detector using the standard Arapuca and also the other light detection system. So let's say the standard configuration of ProtoDUNE. The plot here below show the ratio of the collected light by the X-Arapuca. So the one that can only see the xenon light with respect to the other sensor that can see both liquid argon and xenon light. The light blue band show the different injections, and here on the top you have the amount in ppm. And of course, this is the time. So as you can see, the ratio actually between these two light collected quantities are increasing. And this shows the amount of light that has been shifted for the slow component of the liquid argon scintillation light to xenon wavelength. And you can see that this reach a plateau that is around the 7.7, so the 70%. And these actually correspond to the fraction of the slow component of the liquid argon. So we can say that with this amount of xenon, we can convert basically the entire slow component of the liquid argon. Then the other step is to study the uniformity of the response inside in ProtoDUNE, and this is the injection point. So we used to inject the xenon, the cryogenic line that are used for the liquid argon. So you have to imagine lines on the bottom of the cryostat, but came out close to the APA of one side, and the Arapuca module. The standard Arapuca module are installed, one in the APA 3, so in this position, and one in the APA 6, that is this position. So comparing the lines seen by these two systems, we can see if actually there are differences of the diffusion of this of the xenon insights and the response of the detector. So apart from the light blue bands here again show the time, the injection time, and the injection period. So apart from some scattering at the beginning, this distribution, so the ratio of the light seen by the module installed in these two APAs stabilized, and this is let's say a first indication of an uniform response of the detector. Of course, these are very preliminary studies. There are more deep analysis and more careful quantification that are being developed and will be presented in the future, and we aim to have also a publication soon. Another R&D that I would like to mention is concerning the high voltage. So actually the high voltage system has been pushed beyond its design specific, and the idea was to check what were the margin of operation with respect to the nominal value, and also enlarge any kind of field-dependent study like drift velocity, space charge, etc. So the high voltage system have been set higher at a value of 30% higher of its nominal value, and we record data for 3 continuous days. This is a screenshot of the slow control, and shows the voltage and the current during these 3 days at the cathode. And this actually is a very stable operation, like in a nominal condition. So we did not observe any kind of different behavior of the system with respect to the nominal condition. Another R&D is towards the DUNE calibration scheme. So DUNE is aiming to use neutron generator to test the response to a very low energy particle. And so in ProtoDUNE, we had a period, so a few weeks of data using the deuterium neutron generator. So this was injecting 10 to the 6 neutron per second with a maximum intensity peak at 2.5. So the generator has been located on the top of one APA. And the idea is to see if we can actually detect small blips that may be the signature of the neutron capture. So these kind of blips are the one that I pointed out here with this red arrow, just to give an idea. Of course, again, there are quantitative analysis, more serious analysis. This is just an event display. So you can see so this is the different 3 APAs that are on one side of the cathode. And by eye, we have the impression that we can observe some more blips on this region that are actually is the APA just below the neutron generator with respect to the APAs that are just aside. So this was encouraging, and we are, as I said, doing quantitative analysis, more serious analysis than just eye scanning. There are also some data acquisition development I would like to report. So I mentioned already briefly the fact that during the data taking, the readout of the TPC from Felix has been validated, and during the data taking itself, actually all the APAs have been switched to this readout system. Then there have been development on having a real-time processing system that allow to select a region of interest on real time, so like an heat finder. This is what is shown in the 2 figures here. So this is the real event, and this is the response of this heat finder that we have. And the purpose is to use this heap finder to build a trigger itself. And this is toward the DUNE operation, because the idea is to have the capability to trigger only on region where there are actually some activity and not record the data from the entire detector. And there are also some other R&D to extend the readout window, and there have been the run taken with a readout window up to 1 second that is pretty large. So I come to my summary and outlook. So ProtoDUNE single phase has been recently switched off, so just at the end of July this year. We took 2 years of really excellent data. This experiment actually has been an engineering prototype for the CRYOSTAT design, the cryogenic system, a test bed for the TPC assembly procedure. We studied the performances, and actually we have really excellent detector response. We took data with the cosmic and also particle from beam, hadron beam, and electron beam, and there are physics measurements that are in preparation. This detector has also served as a playground for a test to fully characterize not only the detector design toward DUNE, but also the cryogenic system, for example. And of course, we have many lessons learned. So whenever it was possible, those lessons were being applied on the fly. So during the data taking itself, like for example, the case of Felix, other actually will be applied in the future. Here is a table that compare some of the detector parameter, the ProtoDUNE performance with respect to the specification in DUNE, and this is taken by this paper that is being submitted to JINS, as many of the plots that I presented in the previous slides. And to really conclude, so we are looking forward to the next step, that is ProtoDUNE single phase 2. So this will be a real small scale DUNE module 0 in terms of the detector technology, or so there will be some update for the photon detection system, or also the size of the detector to actually be close as possible to the detector assembly space that will be available on the fire detector module of DUNE. And also the other goal of this ProtoDUNE 2 is to continue data taking with a particle beam, and in this way to enlarge the statistic took 2 years ago, and also to extend it to negative polarity that where data not be able to were not recorded in 2018. And thanks.
Thank you very much, Stefania, for the very nice talk and a lot of information. So are there any questions? If so, please raise your hand through the chat window. Chris says the hand raised.
Yes.
Okay, go ahead.
Physically raised. Thanks very much. I enjoyed that. I actually have a very specific technical question concerning these light guides that were made out of a mixture of various plastics dissolved in acrylic. Is there any information on how well those aged? For instance, if you made this mixture of, I think you said it was toluene, acrylic, and TPB, how did those behave when they cooled down and then when they warmed up? Did they age gracefully? Are they?
Are you talking about the? Sorry, I missed the initial part of.
Well, at the very beginning, you talked about these new wavelength shifting. Yeah, these.
The Arapuca.
Yeah. Okay.
I am not sure that there are very pushed studies about the aging of those systems. I think this is actually a pretty new device,
Right.
I mean, as far as I know.
Right.
I would point you toward this this reference, and probably yes, the further operation of ProtoDUNE.
Okay, thank you.
Fabrice, you are next.
Yeah, so it's also related to, hi, yes, it's Fabrice from Triumph. It's also related to Arapuca, or its comparison in the efficiency, so slide 22. So the size of the Arapuca, yeah, 22. So their size is quite a bit smaller right now. But the number you are giving here, is it normalized by area, or is
So
it?
in this plot, no, but in the response on this plot, I would say yes. So the difference that you see here is actually the difference in the area that is here.
Okay, but so when you compare to a long wavelength shifter bar to Arapuca, you need a lot more Arapuca to cover the same area.
Yes, there is.
So how does that come into this number of 1.2% versus?
So let me get this correct. The number of silicon PM per system are actually the same. So okay, you know, you will lose eventually some energy to the possible knot collection during the light guide here. Mm-hmm. Or for some inefficiency on the dichroic filter here. So yeah.
Yeah, okay, I see. Okay. Thank you. I had another question, but I will let people, yeah.
The number of silicon PM that are used per module, let's say, is comparable. Then, and this makes this comparison, let's say, fair.
Okay.
In that sense.
I don't see any other hand raised. So Fabrice, if you want to, no.
Oh yeah. So, yeah. So my other question had to do with the space charge correction. Yes. So I was surprised that it was asymmetric, but you said that this asymmetry is due to the beam.
No, I mean, so what I was pointing out is that the beam is coming from here. It's just an additional information. This asymmetry is something that we consider coming from the flow, the liquid argon flow that is inside. So I show in one of the previous slides how the cryogenic system is done in for the injection line. So you have the injection of the liquid argon that comes from here. So there will be some flow inside. This is being studied. There are some models. And the modeling actually is close to what we observe on data. It's not perfect. So we are waiting for more development on the liquid dynamic flow. But we think that this asymmetry is basically coming from the internal flow of the liquid argon.
So you're saying that the liquid flow is able to move the ions. So it is comparable to the electromagnetic force or something like that.
Somehow, yes.
I see. So you could flush them out by having big flow.
I don't know if it's really possible to go up to that. But
I see. Thank you.
Jeter, you're next.
Okay. Well, I just had a quick question. That was a very nice overview of the entire project. What did you work on?
So mainly on analysis. So on the preparation of this pion measurement and also some other analysis doing the data taking to understand, let's say, like in short time, the response of the test that we're making.
Okay. So along the lines of space charge, since we have this up, does this have any, and I don't even, maybe this question doesn't make sense anymore, but does this have any impact on the dual phase detector that people wanted to operate?
So, of course, I mean, for the ProtoDUNE double phase, they are exposed to the same kind of problematics. There are studies that are being developed in a similar way that have been done for the single phase. Actually, this is not a procedure new. It's coming from the experience from microBOON, and anything that we learn from one experiment actually is somehow also applied to the others. So for sure they have, I don't know exactly the status of their map, but they have similar studies for taking into account their distortion. I don't know if this answers your question, but it cannot be, of course, these maps cannot be directly applied to the other technology because of the design of the detector inside that is different.
Yeah, I just wondered if it was going to pose a particular challenge to them because they need, you know, a more sophisticated electric field than just drifting.
No, I'm not sure that this may.
Or do they need to drift farther, I guess, to get to the interface?
Sorry, say it again.
Or they need to drift farther to get to the gaseous interface.
Yes. So the drift length is double. Is about 6 meters instead of being 3.5 meters. So this actually make more challenging also the collection of the signal. For the space charge itself, for sure they will not have eventually this kind of distortion, I would say, here in the middle of the volume close to the cathode. Any other differences? I'm not sure. I don't want to say something that is wrong.
Okay. And then on the purity, which is very impressive. I was at Fermilab when Stephen Portis was building this liquid argon purity demonstrator, and people thought it was crazy to start with an argon detector full of air and then just pour argon into it and try to make it into a TPC. So it looked like you're refining what's needed for that purity in terms of, you know, it looked like you were taking a gas pump out because that's not needed. And, it looked like you're just using cold filters now. Is that true?
So what, come back to the to the other slide. So here you're referring to this, the fact that, so this is actually where we had the problem during the data taking. And so the system at the very beginning was designed to have or not have the operation of this pump. So we realized that it actually is possible also to bypass. Honestly, I'm not sure that, so no, yes, this actually has been removed for the double phase cryogenic system as far as I know. So yeah, we bypass this and we go directly on the warm filters.
But the majority of the filtering going from air, well, I mean, first you do the piston push to get a lot of the air out, but the rest of the filtering is done with those cold filters. Is my understanding?
Yes, this is true. So all the gas also that come here that do not go on this warm filter go then on the cold filter, so in the liquid flow.
Do you have any reference on that, details on that?
There is a detector paper that will cover all the cryogenic system and operation that is being prepared. So there is a description of the system that is in the paper that I put the link there, but is pretty concise. And so a more developed description will come soon. I cannot say exactly when, but I hope by early next year, the paper will be at least on archive.
Thank you.
So I see another question from Shimon. Your
yes,
hand appear and disappear, so sorry.
Oh, yes, I didn't want to interrupt Fabrice's comment question. It was a more important one. I have a quick one. Thank you for the talk, first of all. You mentioned some data that you may have been able to analyze, like, for example, regarding seasonal muon flux measurements. Has that been analyzed, published already, maybe?
No, it's not published yet. So there is a nice analysis. So this takes something like set of data for 10 different months. along the 2 years of data taking, and trying to see if there are any changes. So that I know there are measurements coming from other experiments that are the aim, so the measurement that we want to compare to. I don't know exactly when this our analysis will be published, but I really hope soon. It's not let's say far away for having some nice comparison, and so I hope that it'll be out soon, or at least presented in a conference, maybe in winter.
Okay, so I don't see any other question. I would like to thank Stefania again. Thank you very much.
Thanks again for the invitation. It was my pleasure.
And next week on Monday, there is no seminar due to Labor Day, and we will resume September 14 with directional dark matter experiment with Professor Elisabetta Baracchini from GSSI. So again, thanks again.